when any.
All right, it's almost 11 o'clock, so most of you are there somewhere in the room. So let's see, items for this week. Most of this week is going to be centered around the test that you have on Thursday, right? So that should have been on the schedule. Should be aware of that.
Wait,
Pause.
wait, it
Thursday?
says it's on.
I'm sorry.
Oh wait, am I
On the
bugging?
syllabus.
Isn't it next week?
Wait,
I think it's Monday.
Says it's next Monday on the syllabus.
Does it?
Yes,
Well,
Thursday.
please say not this Thursday.
well, okay. I mean, we've pretty much here's the deal is I guess I got confused when I was looking at my own schedule. There you go. But here's my my perspective on it is I think that I wanted to eliminate 9.9 because I just think it's not extra necessary and actually right. My brain is not working right now. Your previous professor, Ruth, was not planning on teaching 9.9, and I wanted to add it in because that's something that I saw. So I was planning on eliminating it and just doing review, and that's what I've prepared to do review today for the test. So if we don't have the test this week, then I'll do a review session today because that's all I prepared for today. But that would mean that I would also cover 9.9, and that would be on the test. So this is your option. You can have the test on Monday as planned,
Next class. I'm prepared.
but there will be an additional section on the test, or we can have
an additional section on the test and actually appropriate. Dear gracious.
What is 9.9?
9.9 is basically
Test.
it's looking at Taylor series and truncating Taylor series and getting bounds on the error and kind of the more applied side of Taylor series.
Like expert question.
Did you say
Expert credit question was a Taylor series.
We need to get a vote. I mean, I could push the test back to Friday, although
Friday, I'm out of town.
right. So I could push it back to Friday, and
I can't
do
do Friday.
Daniel can't do Friday. Okay, we're gonna make sure that we set our schedule to Daniel's schedule. So
Yeah.
On the
Daniel,
test
say it's next
paper, and
Tuesday.
that's planned out the study schedule for like
Oh.
how to study for this test.
okay. So we're going to keep the test on Monday as planned. It's going to cover 9.9. I'm going to do a review session today. Not going to hurt anybody. And then I'll post a lecture that I owe you for yesterday today that will cover 9.9. So you'll be responsible for watching that lecture. And then Thursday we'll have another review session. Wait, no. Hold on. Let me think about this. I'm way ahead of schedule, so that's what's troubling me. We really should have the test this week because otherwise I'm going to start covering stuff that's not going to be on the test, and I mean that might be confusing for you guys. So,
I mean, review days isn't a bad thing.
yeah, well, it is
Really
in
the
terms of
best thing, but
yeah. Well, I mean, I don't want to waste the time. So that's fine. We'll have the test on Monday as planned, and if that's indeed what I have on the schedule, is the 10th the Monday? It is. And I'll just start covering chapter 10 this week, but I'll post a couple. We'll have the review session today and another review session on Thursday, and I'll start this new material on Friday, and you'll have a test on Monday. Does that sound good?
I'm good.
Sounds good. So 9.9 will be on the test since you guys don't want to do the test this week, which is fine. But that means I want to add more material. It's not that much. It's not that big of a deal. It probably only will be one question on the exam. So
it'd be an extra.
no,
Too much,
guys,
yeah.
you don't push it. Don't push it.
There you go.
So I don't know how I ended up so far ahead of schedule. I guess I'm that good, or I'm that bad.
And we're just that off that we won't.
Yeah. But anyways, let's start doing some review. This will all be helpful for the test, and also be helpful before you see 9.9, just to make sure you're firmed up on everything. So it won't hurt anything. But I'm going to be reviewing 9.1 through 9.8 today as much as I can. So we're going to start right at the very beginning, which is sequences. All right. And of course, you're dealing with sequences the whole time. Once you start working with series, you never get away from sequences, but you got to remember how to deal with sequences directly, and what sort of tools and techniques you have for assessing convergence or divergence, right? So it's all, that all is what it amounts to, convergence or divergence. And you have various tests for assessing that, right? So let's look at this first one. So this is just a sequence. We're going to want to look at the limit of this thing as n goes to infinity. And if, you know, we plug this thing in, we just look at what's happening at infinity. This is going to be 1 to the infinity, right? Limit of the interior, since we have a rational polynomial of with the same degree in the numerator and denominator, that's going to converge to the ratio of the leading coefficients, which is just 1 over 1. And then the power goes to infinity. So this is an indeterminate form. Which means always that we need to bust out L'Hopital's rule in order to deal with this sucker. And since we're starting with a discrete sequence, that means we have to make the switch to continuity. So change your n's for x's just to denote that you're switching to a continuous function. So we want to look at this guy. And since we know this is an indeterminate form, or it's an indeterminate power, that's what it says in the book, this guy, we're going to do the whole natural log trick. And if you haven't clued into this already, this is one of my favorite things to evaluate you guys on, because it's tricky and it's a powerful technique. So what do? We say this should be true if and only if the limit as x goes to infinity of the natural log. So we'll get x natural log x minus 5 over x equals the natural log of this limit. Right, I just brought down the x using the log property. And then we have to do a little tweak to get this as a ratio rational function, right? So just looking at the left-hand side, we're going to rewrite it like this. Bringing the x down to the denominator as 1 over x. These two things are equivalent. And, sorry?
Power of x.
What happened? The power of x came down as x using the log property.
Yeah, never mind, I'm tracking.
Okay.
I didn't see the x there.
Yep. All right, so now we have a rational function, and if we look at the limit at infinity, we're going to get the natural log of 1, which is 0, over 1 over infinity, which is 0. So that's a 0 over 0, which we know is an indeterminate form. And this is one of the classic ones, which we can apply L'Hopital's rule to directly, right? So that thing should be equal to, by L'Hopital's rule, the limit as x goes to infinity. And now we're taking derivatives here.
Flip in the numerator.
Yep, we flip the numerator, right? And then we have to multiply by the derivative of that thing. So that's a quotient rule. So that will give us 1 times x minus 5 minus 1 times x yeah, minus x all over the denominator squared. But, oh, sorry. This is a really easy mistake to make. I just did it. So I'm not taking the derivative of this. I'm taking the derivative of this, what is on the interior, so the reciprocal of this. So when I'm taking the derivative of this, it's really important because the quotient rule is not commutative. If I flip the things around, it doesn't work. So that should be the derivative of the top here will be 1, but then I'll be multiplying by x, then minus the derivative of the bottom, which is 1, times the top, which is x minus 5, all divided by the bottom squared. So that's the derivative of the interior of the function. And then we're dividing by the derivative of the denominator here, which is negative 1 over x squared. All right, let's do some simplification. So what it has,
Cancel in the numerator, one of the x's cancel, so it's just x in the denominator, correct?
well, one of the x's cancel here, right? And then we'll get a positive 5. Up here, you have a factor of 1 over x squared. So that's going to cancel here with this 1 over x squared, but there's still a minus sign. So now I have a minus 5. And what's left is x over x minus 5. And then this is something whose limit we can evaluate directly. So ratio of the leading coefficients, we're just going to get minus 5 out of that limit. And then remembering that that this isn't the limit we want, right? This is the natural log of the limit. That means the limit that we want, L, is e to the minus 5. So it's convergent, and we know precisely what it converges to, right? So it is sufficient if you do the computation and you show me the limit, that obviously this implies you have convergence. You don't have to say it out loud. For sequences, it's pretty clear whether it's one or the other. So yeah, that is these problems I really like. I think I've thrown a number of these at you on quizzes now, right? Where you have to use this natural log trick to manipulate it and use L'Hopital's rule. I like it because we're using stuff that we've seen before. We're using the theorem that allows us to transfer into a continuous function. Then we're using L'Hopital's rule and that natural log trick. It's a sweet kind of problem. So questions about that? Nope. All right. Next problem. All right, now we're going to look at the limit as n goes to infinity of this guy. The nth root of 3 to the n over n. Okay. So if we look at the, if we plug in infinity into this thing, then what's going to happen? We're going to have an exponential in the numerator, which is going to outgrow that linear, if we're just ignoring the root right now. So on the inside, because the numerator outgrows the denominator, we're going to get something that's infinite. But that's raised to the 1 over n. Since n's going to infinity, we get infinity to the 0. So that's an indeterminate form, indeterminate power, indeterminate form, whatever you want to call it. So yet again, you're going to need to use the continuity trick. And we will go ahead and write this as 3 to the n over, or sorry, 3 to the x over x, all raised to the 1 over x. And since it's indeterminate power, indeterminate form of a power or whatever, we're going to use that log trick once again. Starting to see a theme here. So we'll just jump right to it. What's that going to say? We're looking at the limit as x goes to infinity. We'll bring down the power, and then we'll have the natural log of 3 to the x over x. And very similar to what we just did, we can write this as a ratio. And now when I plug in infinity, I'll get infinity over infinity, which is an indeterminate form that we can use L'Hopital's rule on directly. So using L'Hopital's rule, we'll take derivatives. Very similar to last one, we're going to flip that guy on the inside of the natural log and then multiply by the derivative of that. Yet again, it's another quotient rule. So derivative of the top is natural log of 3 times 3 to the x. And then we're going to multiply that by x, because that's the bottom term, minus the derivative of the bottom, which is just 1, times the top, which is 3 to the x, all divided by the bottom squared. And that's all over 1, since we took the derivative of x. All right. So we're looking at this limit. Now let's do some cleanup. Let's see, I can factor a 3 to the x out of the numerator here, and that's going to kill this 3 to the x. So gone, gone, gone. Likewise, I've got an x here and an x squared there, so that will eliminate one of the x's. So what's left, we have natural log of 3 times x minus 1 all over x. So this is a just a rational polynomial whose degree in the top is 1, degree in the bottom is 1. So it's going to converge to the ratio of leading coefficients, which will just be the natural log of 3. And yet again, we're going to translate this back into what we want. So that says the natural log of our limit is equal to the natural log of 3. Therefore, our limit is 3. So both of those sequence problems require the same machinery. I think you can count on there being something like this on the exam, because I like it. Okay, any questions about that? Both of these techniques are algebra intensive, obviously, and you have to take these derivatives. So it's a great one to test your former knowledge, right? What your algebra skills are and what your derivative taking skills are. So I like it. Any questions?
This is a minor one, but how do you do quotient rule? Like, how do you write it? Because the way I do it is the first times the derivative of the second, or sorry, no, the second times the derivative of the first minus the first minus the derivative, or the first times the derivative of the second, all over the second squared.
Yeah, so the
How you do that?
the quotient rule, you know, you may have learned it one way or the other. But the most critical thing about the quotient rule is that you're always taking the derivative of the numerator first. It's very important because there's a minus sign in the formula. If you flip it, then you're going to be off by a sign. So that's the only thing that I think is critical, is you just remember you're taking the derivative of the top times the bottom minus the derivative of the bottom times the top over the bottom squared. You know, whatever the ordering here doesn't matter. This is commutative. If g times f prime is the same as f prime times g, doesn't matter. But what does matter is that we're always taking the derivative of the numerator first. Get that minus sign right. Any other questions? Nope. All right. Let's cruise. All right. So leaving sequences behind, although they're always with us in spirit, because we often are looking at series in terms of their corresponding sequences. So let's go. So at this point on the exam, you will not be given prompts for what technique you should use. One of the reasons is that you can use any number of techniques in some cases. So there's not necessarily only one path to the solution, but all roads, at least all valid roads, lead to Rome. So if you use good math, you'll get the right answer.
All paved roads.
Sorry?
All paved roads.
All paved roads, sure. Yep. If there was an infrastructure project, right, that built a road to Rome, then we've got such a road. So I'm not going to specify which technique to use. You're just going to be handed a series and say, is it convergent or divergent? And there's a number of different ways to do that. Sometimes there's a better way, but as long as you take one of the paved roads, you will always get to the right answer. So let's do this a little bit more collaboratively. Does anyone have any instincts about what we should do here?
I think if you do partial fraction decomposition, it will turn into a telescoping series.
Correct. Yep. So this one should be one that you've seen before. We can do a partial fraction decomposition on this thing and hopefully get a telescoping series. So you're never going to get away from partial fractions. So partial fraction decomposition. How we set this up? A over n plus b over n plus 1 should be equal to all of that. So that's going to tell us that -2 will equal a times n plus 1 plus b times n. And then, you know, I like to do equating coefficients. So we'll have a plus b times n plus a, which gives us a system of equations in the coefficients. We know that a plus b must equal 0 since there are no n terms on the left-hand side. And we know that a must equal -2 because that's the only constant term. Once we know a equals -2, that gives us b. So we've got a, we've got b. So now we're looking at the series starting at 2, going to infinity of, I'm going to put the negative in the back. I mean, we can do it either way, but just usually it looks better. So b over n plus 1 minus a over n. So we've rewritten our series in this form, which looks very much like a telescoping series, right? Because we are taking a difference, always need a difference for a telescoping series. And one of the terms is ahead of the other term by some amount. Usually it's 1, but it could be 2 or it could be 3. As long as one's ahead of the other one, then we should end up with something that's telescoping. So now we'll look at the nth partial sum of this guy. We're starting at 2. So as we start to sum, we plug in 2 first, and we'll get 2 over 3 minus 2 over 2, which is 1, plus 2 over 4 minus 2 over 3. I'll come down here, plus the next one we're plugging in 4, so 2 over 5 minus 2 over 4, and so on and so forth until you get to the nth term. Now, it's very important that you actually do this step because sometimes the telescoping series are wonky. And this is one of the cases where it's not the first and the last term that survive, but it's the second term and the second to last term that survive in this case. So we have a 2/3 here, cancels with the 2/3 here. We have a 2/4 here, that cancels here. So we're gonna have all that cancellation, and this term is ahead of this term, right? Because it's n instead of n plus 1. So that's the one that's going to die. So the only one that's left, the only terms that are left are the minus 1 and the 2 over n plus 1. So I'll write it like this, 2 over n plus 1 minus 1. And then we're taking the limit as n goes to infinity of that guy. And the leading term there will go away, right? It will converge to 0. So all that's left is -1.
Version on -1.
Yep. So our series converges to -1. The telescoping series are always nice because, yet again, I get to test your algebra, right? You guys, a lot of you struggle with partial fractions on the last exam, so now is the chance to redeem yourself. I'll definitely throw one of these on the exam. Be prepared for it. Sorry, what?
I have a question for.
Yes.
So for partial fraction decomposition, we're basically just cross multiplying, right?
Are you talking about how we go from this step to this step?
Yes.
Yeah, so we're just taking that whole denominator and we're multiplying it up by everything here, right? And so what always happens is one of the terms, you already have one of the factors in the denominator, which is going to get eliminated. So, if the a is with the n, then when you clear out the denominator, it's always going to get the other one, right? It doesn't have an n, it has an n plus 1, because the b had the n plus 1, and it'll get the n. But go ahead.
They cancel each other out, basically.
Yeah. You cancel out the common factors, and you're left with whatever's you're left with. For a more complicated partial fraction decomposition, remember that you'll have powers of linear factors, and so it could be more complicated. But with these telescoping series, it's usually not that complicated. Any other questions? Nope. All right. Okay. So we're handed this series. And determine convergence or divergence of the series. So what to do? Well, remember the standard protocol is to determine whether you have absolute convergence. If not, then you look at conditional convergence, right? So the first thing we're going to look at is absolute convergence. So we want to look at this series. We already know that our VIT is satisfied, right? Our very important theorem, because the 1 over natural log of n plus 1 definitely goes to 0 as a sequence. So we don't get any traction there. So we need to look at this guy. All right, so you have lots of different tools in your toolkit. As I've stated before, I think you get a lot more mileage out of the direct comparison test, generally. Limit comparison test definitely comes in handy, but that's usually the first thing I look at is the direct comparison test. And the one thing that we know about natural logs is when we're doing comparisons, we know that we can compare it to any power of its argument, and it'll always be less than that, right? So in particular, I could say this is less than n plus 1, which is n plus 1 to the 1. If I do that, then this guy, since it's a reciprocal, will be strictly greater than 1 over n plus 1. All right. And also, you always want to kind of test your intuition. You look at this guy and you say, what do I expect it to do, converge or diverge? Well, I know that the natural log is one of the slowest growing functions out there. It grows slower than n. And you know that 1 over n as a harmonic series is divergent. So this thing should be divergent. That's our expectation. And so now we're comparing it to something that looks like 1 over n. And if I'm looking for divergence, then I need a greater than here, right? I want this to push this to divergence. So this needs to be below it, and it pushes it. So that's great. It does seem to show divergence, but we have to actually prove it. And we don't know about this series directly. We want to say this is divergent, therefore this is divergent by the DCT, but we don't know about this guy. So how do I show that this is divergent? Well, it'd be great if I could compare it to 1 over n. There's a couple different ways we can do this. One is we could do an integral test. So this is I'm going to make a point here of showing you how you have multiple roads to a solution. One thing we could look at is the integral from 1 to infinity of 1 over x plus 1 dx. Just like with the continuous function theorem, I have to convert this into something continuous in order to integrate it, right? So do not put n's in here or you're going to get in trouble. If you want to use the integral test, you need to convert to x's. So I know you understand that we're dealing with a continuous thing. And using a kind of basic u sub here, this is the natural log of x plus 1. And then we're evaluating it from 1 to infinity, which we know can be rewritten as a limit as b goes to infinity of the natural log of x plus 1 from 1 to b. And that is going to get us the limit as b goes to infinity of the natural log of b plus 1 minus the natural log of 2. And as b goes to infinity, b plus 1 goes to infinity, which means the natural log goes to infinity, which shows divergence. So what does that say? that says that this series diverges, right? If the integral diverges, then the series diverges. And if this series diverges, we have a string of arguments here. We say, hey, this one is divergent by the integral test. Which implies that this one is divergent. By direct comparison. So that we're using the integral test to prove this is divergent, which then in turn proves that this thing is divergent. And so in other words, this thing is not absolutely convergent. So all we've done so far is just proven that it's not absolutely convergent. You could have just as easily proceeded using the limit comparison test and gotten the result that way. I went for the integral test. I don't think maybe this is more complicated. I don't know. It just depends on your feelings about integrals. So if you don't like this, then try the limit comparison test. You'll get the same result. So all we've done is prove that it's not absolutely convergent, which means we need to look at conditional convergence. All right. So if we're looking at conditional convergence, then we need to look at the properties of this guy. What do we need? We need, our bullet points are, we need this to be positive. That's a check. We need it to be non-increasing. And that is always the hard one, or potentially the hard one. So what would that say? That would say that 1 over the natural log of n plus 2 should be less than or equal to 1 over the natural log of n plus 1. So it gets fairly clear that we can say this is the same as this. And the denominator is always smaller than the numerator. We could have flipped it around. Maybe that would be a clearer way. So let me do it that way. If that's not clear to you, this is the same as asking, is this true? And clearly, n plus 1 is less than n plus 2. And since the natural log we know is monotonic, non-decreasing, shows that this is true. Right? Natural log is monotonic, non-decreasing. Therefore, the reciprocal of it is non-increasing, right? Which is what we need. So that gives us what we need there. And then the final thing is we need Bn to go to 0, which is a check. So that implies that we have conditional convergence by the alternating series test. But you do need to explicitly check all the properties. And obviously the one that requires the most work is the second one there. You got to make some clear argument there. Somehow you have to show that the two things are always, it's always true. Sometimes it's really obvious. Sometimes a little manipulation like this gets you to a statement that it's hard to argue with, right? So yeah. So that's a good one. We've got non-absolute convergence, but we have conditional convergence, and I threw in an integral test just to round everything out. So We're using all the tools that we have in our toolkit. Any questions here?
The second inequality, with the error, the question mark above it, is the first term's n+1, right? It's kind of hard to see.
Right here?
Or the second one with the question mark to the right. Yeah.
N+1, yep.
Okay.
All right. Always more series. What my time is looking like. We got 10 minutes. So we will be doing more here. I think I can squeeze 2 in here. So I'll be doing a whole nother lecture of review. So don't worry if you feel like I haven't covered something. I don't know how many I've done at this point, but we'll look at this guy. Series from n equals 1 to infinity of 1 over root n times n+1, n+2. All right, so you look at this guy, you squint at it, and you say, what does this basically look like? It basically looks like 1 over the square root of n cubed. Right? You have a third order polynomial inside of a square root. As n gets really, really big, the smaller terms kind of don't matter. So this is basically what it looks like. So that gives us some, at least some place to start when it comes to solving this thing. So how about we do a limit comparison test? So we're looking at this one. Over this one. Remember, limit comparison test, it looks a whole lot like the ratio test, but it's not. So don't get confused. There are no absolute values. We're not incrementing by 1. It's just the limit comparison test. And remember, with the limit comparison test, you're comparing it to the sequence to some other sequence. And the way it works is the corresponding series for this sequence, whatever it does, if it diverges, then if this whole thing converges, then the series that goes with this one also diverges. Likewise, if this converges and the whole thing converges, then the series converges. So it goes as the thing that you're comparing it to. And what do we know about this guy? Is it convergent or divergent? The thing I'm comparing it to.
Thanks.
Series.
What is square root?
Can you hear them?
It sounds like mumbles.
It should converge because it turns into n to the 3 over 2, which is greater than 1, right?
Good. Yeah, so it's a convergent p-series, right? So we're comparing it to a convergent series. Therefore, we're expecting that if this limit converges, then the series converges. So let's see what happens. When I flip this over, I can just rewrite it all as this. N cubed over n times n+1 times n+2. And I can just have one big square root there. And on the interior, what do we got? If I were to expand out the denominator, I'm going to get a cubic polynomial. So the leading power will be n cubed, and the coefficient of n cubed will just be 1. I don't care about the other stuff. So, I can write this basically like, this is going to equal this over n cubed plus stuff of a lower order. It doesn't matter. This stuff is all of a lower order. So I'll say stuff of lesser degree. So when I go to evaluate this limit, it only depends upon the highest powers. They both are the same. Therefore, it's the ratio of the leading coefficients. So the limit on the interior will just be 1, and then we take the square root, so we'll get 1. So the comparison sequence converged. Therefore, since we're comparing it to a convergent series, that must mean that this series converges. So this is convergent by the limit comparison test. All right, any questions about that? Okay, I'm going to try to squeeze one more in. Here we're looking at a power series. And I wanted to bring this one up because I realized that I've been using some terminology incorrectly, and I want to be clear about what the terminology is for power series. And I'll make sure to emphasize this in the other review session too. So, right. So we want to, we know that we want to find the so-called radius of convergence for these guys. And then there's also something called the interval of convergence. And I've been sort of loosey-goosey about this. So I want to make sure that it's clear what is what, because there's two different things here. We know that if we want to find the the radius of convergence, we're going to use the ratio test on this guy. So increment it by 1 in the top, divide it by the 1 in the bottom, and you're going to get a lot of cancellation, which is the hope. So we'll end up with an n in the top, an n plus 1 in the bottom, and then there's going to be a 3, right? A 3 that ends up in the bottom as well, from 3n divided by 3n plus 1. So you end up with 1, 3, and then we'll have a absolute value of x plus 4. We take the limit of this thing, and the n over n plus 1, that goes to 1. You still have a 3 there. So you're going to end up with the absolute value of x plus 4 divided by 3. It's coming from here. And we need this to be less than 1 in order to have convergence. If I rearrange that, that says that the absolute value of x plus 4 must be less than 3. And here's where I have to make an important point that I haven't made clear enough, or at least just sort of garbled this in the lecture. So this is a power series centered at -4. So when I get down to an expression like this, this shows me that the radius of convergence is 3. So the radius of convergence, which is r, It's just a number, and that's this number here. So I look at the power series, I say, where is it centered? And can I drill it down to some expression where I'm looking at the absolute value of x minus its center, and whatever that has to be less than in order to get convergence, absolute convergence, that is your radius of convergence. So I've been confusing radius of convergence with the interval of convergence. They're two different things. So radius of convergence is just this number, okay? You have to find this number along the road to finding the interval of convergence. So there's nothing really, you're not doing any extra work. You're just having to make a distinction in your head that once you get to this step, when you're finding that interval, this tells you what your radius of convergence is. So if I ask for the radius of convergence, I'm asking for that number. If I'm asking for the interval of convergence, that's when we do the whole thing where we find the interval and test the endpoints, right? Whatever we get at the end of that analysis, that's the interval of convergence. So now we know the radius of convergence. Now we look at the interval of convergence. So we can rewrite this as a compound inequality, which says that x must be between -4 and -7. So this is a radius of absolute convergence. We know that as long as we're inside that open interval, we have absolute convergence. Now we have to test the endpoints. So what happens at x equals -1? We plug in -1 into the series up here, and we get the series. You plug in -1, you'll just get 3 to the n. It'll cancel out with the other 3 to the n. So you're just going to get a harmonic series, which we know is divergent. If we test at x equals -7, then what are we going to get? We're going to get, when we plug in -7 up there, we're going to get a -3 to the n. So we can pull the -1 out of that, get a -1 to the n. The other 3 to the n will cancel, and we'll get -1 to the n over n, which is an alternating harmonic, which we know is conditionally convergent. So if we put it all together, I think you guys can still see that, right? So the interval IOC, the interval of convergence, which I've been inappropriately calling the radius of convergence, the IOC is -7 inclusive up to -1 exclusive. So it's that half open interval, or in topology, we call it a Clopin interval, half closed, half open, Clopin. So that's a terminological distinction. You really aren't doing any additional work, so don't freak out. You just need to make the distinction. Who is the radius of convergence? It's that number that you can make the absolute value of x minus the center less than. Who is the IOC, or interval of convergence, is what you get from this analysis that you have to do. So find the interval and then test the endpoints. That will give you the IOC. Okay, so sorry for going over, guys. I will post another lecture today going over 9.9, and then we'll do another review session on either Thursday or Friday. You guys can make your pick, and then we will have the test on Monday, and we'll also be starting on 10.1 this week. So thank you for your patience.
Thank you.